Okay. So as you see on the title, I have two things to talk about today. This is logarithmic differentiation. I have written optional. This is not included in the book, but I think it's very useful if you know it. If you want, you can use it in the exam, no problem. Okay, but you don't need to learn it if you don't want to. And the second topic that I want to talk about is called the related rates. If you remember, I talked about the applications of the chain rule. I talked about that, but I just gave you one example. Now we are at a position that we can solve more interesting problems. So again, nothing new is here. I have already taught about that, but I will give you more examples today. And these are examples usually at the level of the national exam, but of course the national exam is also canceled. Apparently I received an email from Daniel exactly right now. I don't know when they are talking. Are they talking about? I haven't read the message yet, but I just want to know that it is expected from you to know about these things when you are finalizing at 4. Okay, so let us see what is the logarithmic differentiation. And these examples, I have chosen all of them from this book, Calculus, a Complete Course, 9th edition, 2018, Pearson, written by Robert A. Adams and Christopher Essex. So this is a very famous course book for you, especially when you go to technical university. That would be your course book. Okay, so here we want to, a function is given to you, and you are supposed to find a derivative, as simple as that. In principle, you really don't need any new lesson to differentiate this because you know what to do. Yes, this is a fraction. What you need is a quotient rule. So you need to know what is the quotient rule. If you remember, we talked about this last time. So this is f prime times g minus f times g prime divided by g squared. So here, this will play the role of the numerator, this play the role of the denominator. So in principle, I can start differentiating right away by using the quotient rule. But when I come to the derivative of the numerator, the derivative of the numerator is a product rule with 3 functions. So I need to take the derivative of the first one multiplied by the second and the third one plus the first one and the third one multiplied by the derivative of the second one plus the first one and the second one multiplied by the derivative of the third one. And after this is finished, I need to multiply it by the denominator and then subtract the whole thing from the derivative of the denominator to power 2. It's not that tedious, at least for these very simple polynomials, but it is more or less, it takes time. But if you know logarithmic differentiation, the method of logarithmic differentiation, it would be easier, especially if you know the properties of logarithm very good. So what you do, the first thing that I want to just solve the problem, then you will understand what the method is. So here I would write y equals to, so let me do it exactly. You don't need to write y. So let me just write f of x. F of x is equal to this. The first thing that I do, I take absolute value from both sides, yes? So, but then I hope that you remember these rules from absolute value. If I have absolute value of a number divided by another number, I can write it as the absolute value of the numerator divided by the absolute value of the denominator. And then if I have absolute value of the product of two numbers, I can also write the absolute value of the first one multiplied by the absolute value of the second. The reason that I am taking absolute value from both sides becomes clear shortly, yes? So if I take absolute value according to these rules, it becomes absolute value of the first item, absolute value of the second item, absolute value of the third one, divided by the absolute value of what is written in the denominator. Hopefully it is clear. In principle, I should put absolute value here, but this is a fraction. It becomes absolute value of the numerator divided by absolute value of the denominator. But then again, the absolute value of the product becomes absolute value of the first bit, absolute value of the second one, absolute value of the third one. I did it in one go actually here. So that is reasonable. The reason that I am doing this because my goal is to take ln from both sides. Okay, so I am saying that if this is what you are telling to me, you have to admit that this is the absolute value of that, and then I am taking ln from both sides. But do you remember, how can I write the ln of this? Ln of a fraction is equal to ln of the numerator minus ln of the denominator. Ln of x times y is equal to ln of x plus ln of y. Yes? So let me write everything in steps for the first time, but you can do it much quickly. This is why it is very efficient. In principle, if you want to be slow, you can write all these steps. It's good for the first time to understand what's going on, and then you can do it quickly in your head. Okay, so if you want, I can put a pair of brackets around that. But then what I can write, I can say that, okay, the ln of absolute value of f of x is equal to the ln of the numerator minus ln of the denominator. But ln of the numerator itself is a product. So it becomes ln of the first one plus ln of the second one plus ln of the third one. So hopefully it's understandable that this becomes ln of x plus 1 plus ln of x plus 2 plus ln of x, absolute value of x plus 3 minus the ln of what is written in the denominator. Please let me know if you have any questions so far. The reason is not clear yet why I am doing this, but please try to understand that the process is acceptable for you. Okay, now if you remember, let me remind you of something. Do you remember I told you that this formula is given in the book, that ln of x prime is 1 over x if x is positive. But I told you that this is also valid if I have absolute value of x and then prime. This becomes exactly the same formula 1 over x, but the good point is that it also works for negative values. Okay, so the only restriction in this formula is that x shouldn't be 0, but there is a very big restriction here. X cannot be negative. It's clear because in front of the ln I cannot put a negative sign. But if I have absolute value, I don't need to be worried about negative values because absolute value will turn them into a positive number. The only thing that I need to care is that ln of 0 is not defined. So it means that if I want to write the chain rule version of this, the absolute value of u prime, it follows the same rule. It becomes 1 over u, but you need to remember to multiply by u prime. And the restriction is that u is not equal to 0. Okay, so if we accept that one, so I start differentiating now. How? I differentiate the left-hand side. I also differentiate the right-hand side. Yes? And now, if I ask you what is the derivative of this, you can exactly use this rule. It becomes 1 over f of x multiplied by f prime of x. So if you don't mind, let me write f prime of x on top. And if I ask you what is the derivative on the right-hand side, it is very simple now. Because this is the sum and difference of functions. It's not a product. It's not a quotient. So I don't need the product rule. I don't need the quotient rule. What I need is just the sum and difference rules. I take the derivative of this one, which I will follow exactly this rule. So it becomes 1 over x plus 1. Why I said 1? Because u prime in this case is x plus 1 prime. X plus 1 prime is just simply 1. So the next one is also for the same reason becomes this. The next one also becomes this. And the next one becomes this with the negative sign. But what was my goal? My goal is to calculate f prime. This is what is missing for me. Then the idea is clear. Can you tell me what should I do to find f prime?
We multiply both sides by
Exactly,
f of
thank
x.
you. Exactly. So f prime of x becomes f of x, but f of x is given to me. X plus 1, x plus 2, x plus 3 divided by x plus 4 multiplied by this package 1 over x plus 1, 1 over x plus 2, 1 over x plus 3 minus 1 over x plus 4. That's it. That's my derivative that I was looking for. If you want to, of course, you can multiply this here, then this one and this one will be cancelled. You don't need to simplify. If you want this, if all you want is the derivative, that is your derivative. And if you are a little bit quick, this is much more efficient to do these things. So do you understand the essence of this calculation? Because I will give you more examples from the same book. It's good to see them in practice. No questions? Okay, so let me give you another example. This function is given to you. You are supposed to calculate g prime of 1. G of x is given to you. Of course, you don't really need a new method. You have everything at your disposal to be able to solve this. So do you remember? You will take this one to be your u, and then you will have a square root of u prime. So it becomes 1 over 2 square root of u multiplied by u prime. Okay, but the u prime thing is a product rule with 3 functions. So you need to write, be patient and do it. Of course, if you do it, that's okay, it will be done. But I want you to teach you logarithmic differentiation. So the first thing that I need to do is to, here we don't need the absolute value because g of x is automatically non-negative, yes, because I have it as a square root sign. So what I do, I just take ln from both sides. So this is the part that you need to do it quickly. If you are good with ln's, then it would be efficient. Otherwise, you might lose a lot of time to do that as well. So do you know what should I do? I hope that you remember this formula. If I have something ln of the box to power p, what can I do with this box p? I can put it in the back of the ln, yes, and write it like this. And if I have a square root of a box, I can write it as box to power 1 over 2. Yes, so the first thing that I do, I can write it as this expression. I can write it as x plus 1, x squared plus 1, x to the 3 plus 1 to power 1 over 2. This power 1 over 2 will go back, and then I will face ln of a product, but ln of a product can be expanded as ln of as the sum of ln's, yes? So this is why I'm saying it's better to do it quickly, otherwise you will lose a lot of time. So if you don't understand it, please let me know then. Is that understandable for everyone that ln, taking ln will give rise to this? Yes?
Yes.
Okay, so good. If you understand that, that's good. Then I can start differentiation. The derivative of the left-hand side becomes simply g prime of x divided by g of x, as I told you before. The derivative on the right-hand side is super simple now because it becomes 1/2, it's a constant. The derivative of the first one is the derivative of x plus 1, which is 1, divided by x plus 1 itself. The next one becomes the derivative of x squared plus 1 is 2x divided by x squared plus 1. And the derivative of the next one is 3x squared over x cubed plus 1. Yes? All of them, I am using this rule. ln of u prime is u prime divided by u. Actually, I am done now. This is my derivative, as simple as that. So g prime of x is equal to, I multiply both sides by g of x, but g of x is this guy. Even though it seems still horrible, but who cares? We found the function, the derivative, yes? And then the question is simple because I want to calculate the derivative at a single point. Yes, so I would write everything here. If you want to be patient and write everything down. X3 plus 1. This is your derivative, but what is wanted from you is to calculate g prime of 1. So it means that now I substitute 1 everywhere. So let me do most of it in my head. So if I put 1 here, this becomes 2, this becomes 2, this becomes 2. If I multiply them, it becomes a square root of 8, which is 2 square root of 2. This 2 and that 2 are cancelled, so I have a square root of 2. Multiplied. If I put 1 here, it becomes 1/2. If I put 1 in the next one, it becomes 2 divided by 2, which is 1. So let me write 2 over 2. And the next one, if I put 1, it becomes 3 over 2. And then if I add them, 3 plus 2 plus 1 is 6 divided by 2 is 3. So you see, I'm able to calculate this quite fast. 3 square root of 2. Of course, if you use this method, I will not give the questions like this so complicated. But I mean, even for the simple ones, if you want, you can use that. But this is optional. I will not design questions that you have to know this method to be able to solve the problem. But if you know it, you can use that. Is there any question? So now, if you don't mind, let me give you another example from the same book. Wait for you a little bit to do it, then I will quickly go to the next example, okay? So this is the next example that I want you to solve. So I pause the video at this point if you are interested to learn this method as well. Okay, any one of you got the answer?
I'm still calculating.
Okay. So I can give you a little bit more time. Okay. So let me I probably forgot to say why we take absolute values in the first place. Let me go to the previous slide here. So you see here, I was talking about the derivative of the function at x. I don't know what the value of x is, so I don't know if this is positive or negative, positive or negative, positive or negative. The same for x plus 4. So it means that I am not in principle allowed to write ln of x plus 1 because in this function, what is important, you see, in this function, am I allowed to have x plus 1 negative? Yes, of course, there is no restriction here. But when I write just ln of x plus 1, if I want to be very clear about everything that I am doing, I need to make sure that what x plus 1 is positive. Yes, so I don't, you see, here, I don't have any restriction to have x plus 1 to be positive. So in principle, x plus 1 could be negative as well. But if x plus 1 is negative, then I will have problem here. This is why first I take the absolute value to guarantee that what appears in front of ln is a positive number. And fortunately, there is no difference between the derivative of ln including absolute value or not including absolute value. So this is why in this example, probably I forgot to say why I'm taking absolute value in the first place. But in the second slide here, we don't need to take absolute value because, not because of this one is positive. I thought about that a little bit. Here I am talking about the derivative at point 1. Close to 1, because you remember the derivative is a limit process and you will send your variable to that number. So close to that number, this is not negative, this is not negative, this is not negative. So because here I am calculating the derivative at a point so that I can manually check that none of them is negative close to that point, I don't need to take the absolute value sign. That is the main reason. Okay, I need to correct that when I was thinking about this a little bit more. Now here the same situation happens. In principle, this can be negative because this is the third root. The third root, I don't have any problem with putting a negative number below it. So in principle, this can be negative. But in this case, I don't need to bother to put absolute values first and then do the calculation, because I am supposed to calculate the derivative of this function at the given point 0. For 0, this part is positive, this part is also positive, and this part is also positive. So I don't need to bother about that. That is one comment about absolute values. So here, I can directly start taking ln from both sides because I know I am doing differentiation around 0. So this is the important part. If this is going to be useful for you, you need to be quick in writing this. Let me write it quickly, and if you don't understand, let me know. If I want to do it correctly, I will definitely immediately write it as this. Okay, now I want to make sure that you understand what I am doing. Let me explain it now. Here, I have a fraction. When I take ln, I have to take ln of the numerator, but the numerator can be written in this form. And minus ln of the denominator. Yes? But then this is a product, so I would write it ln of the first one plus ln of the second one minus ln of the last one. But now this power goes behind this, I will get this. This power will go behind this, I will get this. And this power will go behind this, I will get this. So the whole point is that try to do it immediately. Don't spend time on writing all these steps unless you want to practice to understand. But the point is to do it quickly. Is there any question now why the left-hand side is equal to the right-hand side here? And it is doable. You see, it was easy to write this immediately. When you write this immediately, you take the derivative from both sides. According to the chain rule, the left-hand side becomes h prime of x, over h of x. The right-hand side, I have 1 over 2. You know what to do with ln. This goes in the denominator. You take the derivative in the numerator, which is 1. You go to the next one. You take 1 minus x to the denominator. You differentiate this in the numerator, it becomes minus 1. Then you have minus 4 over 5. And then you have this now. 1 plus 5x goes down, and then you differentiate this one, it becomes 5. You see, it is very, very simple in this way. Okay, now what I need to do, I need to calculate h prime. So I have to multiply everything by h of x. Even if you don't need to bother to write it. Okay, you just write h of x and try to see what is going on here. So it becomes 1 over 2, 1 plus x minus 1 over 3, 1 minus x. And then this one, 5 and 5 are cancelled. So I will get minus 4 over 1 plus 5x. Now, what is my question? My question mark is h prime of 0. So it means that I put x equal to 0 everywhere. And then calculate. Okay, so this means that h prime of 0 is equal to h of 0 multiplied by, if I put 0 here, it becomes 1/2. If I put 0 here, it becomes minus 1/3. And then the other one becomes minus 4. But if I ask you what is h of 0, that is also simple. What you need to do is put 0 here, 0 here, 0 there. the numerator becomes 1 times 1 to power 1/3 divided 1 to the power of 4/5. But this becomes exactly 1 again. So this is nothing except 1. And if you calculate this number using the common fraction, yes, you will get minus 23/6, and then you are done. So you see, this is horrible if you want to calculate this using the product and the chain rule. But I really recommend you to be able to do that, because this also will teach you a lot to improve your skills when differentiation. Yeah, try to use your chain rule knowledge, product rule, and that quotient rule to solve this problem, and then you can compare how tedious would be the other method. Okay, but as I told you, that this is optional. If you don't want, you can just ignore that. Okay, good. Okay, so let us see what we have the next. So this is finished. This was optional, but this I expect you to know. Okay, this is, I told you again, these are examples related to that part that I just only solved one problem for you there. Okay, application of the chain rule. So here, let me read the question first. This is also chosen from the same book. How fast is the area of a rectangle changing if one side is 10 centimeters long and is increasing at a rate of 2 centimeters per second, and the other side is 8 centimeters long and is decreasing at a rate of 3 centimeters per second? Okay, this is a very simple but very instructive example, I would say. You will understand a lot about these rates of changes and everything. So here, assume that, let me solve this one at least for you, and then you can think about other problems yourself. Yeah, these problems could be quite hard sometimes, okay, but not at least this one. I think this is not a good ratio, 8 and 10. So so 1, 2, 3, 4, 1, 2, 3, 4, 5 is a better one if I can remember it. So 1, 2, 3, 4, and 5. So oops, this is the bad point about keeping this and counting. Yeah, okay. I think that's correct. So assume that you have this side 8 centimeters, and then you have this side 10 centimeters. Okay, but this is not a fixed rectangle. Okay, this side is increasing at a rate 2 centimeters per second, and this side is simultaneously decreasing at a rate of 3 centimeters per second. The point is that how fast is the area of this rectangle changing? Okay, I don't know. Do you have any intuition? Do you think that the area will increase or decrease with these numbers? Let us see what happens at the end. But how you need to solve the problem? If you want to solve the problem, you need to find your target function. Your target function is the area of the rectangle. So you need to write a formula which expresses the area of the rectangle. So how can I do that? It's simple. Let me call it area, A. It is equal to the, for example, length multiplied by width. This is what we know about the area. But of course, it is clear that the length is not fixed. It is changing over time. The width is not also constant. It is changing over time. One of them is increasing, the other one is decreasing with different rates. Okay, so it means that how you interpret this equation is that, of course, A is directly a function of L and W, but L itself is a function of time. W itself is also a function of time. So at the end, I can say that A is also a function of time, but not directly. A depends on two variables, L and W. L itself depends on time. W itself also depends on time. So it means at the end of the day, my area depends on one quantity, and that is time. Okay? Here, by how fast, you need to understand they are asking you about the rate at which area is changing over time. This is the terminology. When we say how fast, we mean the rate over time, the rate of change over time. So it means that what is wanted is the derivative of the area with respect to time. Do you remember? I go back again to Leibniz notation, which is more suitable in this context. This is my question mark. When, let me read the information again. When one side is 10, for example, the length is 10, at that time, yes, and the width W is 8 centimeters, exactly at the moment that I am looking at a problem. So in principle, if you want to be very, very precise, you need to write L at a specific moment where this is 10, and width at the specific that specific moment when W is 8, and then you are asking what would be the rates of change at that particular moment. Okay, but you don't need to write these, you're very so strict. This is the information that you have, but let me translate the rest of it. The length is increasing at a rate of 2 centimeters per second. So it means that dl dt, this is the rate at which the length is changing, is positive 2 centimeters per second. Why positive? Because it's increasing. And the other side, which is the width here, is changing over time by a rate of 3 centimeters per second. But because, sorry, it's mentioned that this is decreasing, you have to put a negative sign here. Any questions so far? I am just translating these English sentences into mathematical notations. Okay. This problem we couldn't solve at that point because we didn't know about the product rule. Why we need the product rule? Because I want to differentiate this function, but this function is a product of two functions. Why they are functions? Because this depends on time, so that's a function of time. This is also a function of time, so that's a product of two functions of time. Okay, so if I want to differentiate this, how should I do that? I need to use the product rule. So do you remember? The derivative of A with respect to time means the derivative of this product with respect to time, but the derivative of the product is the derivative of the first one multiplied by the second one itself, plus the first one multiplied by the derivative of the second one. Now everything, this is my question mark, and everything I have it. What is dl over dt at that particular instant of time? It's positive 2. Multiplied. At that instant of time, w is given to be 8. So I would write 2 times 8. Okay, so if you want to be very like physics, so you need to write the units, but I prefer to write the units at the end, even though this is technically wrong. So let me just be very precise here. So dl over dt is 2 centimeters per second multiplied by w, which is 8 centimeters, plus the length is 10 centimeters, multiplied by minus 3 centimeters per second. In principle, you have to include the units, but that is, I'm too lazy to consider that, but I have to write the units, the proper units at the end. Okay, now let me tell you what happens. 2 multiplied by 8 becomes 16, and then centimeters multiplied by centimeters is centimeters squared over seconds, and then I will have minus 30 again square centimeters per second. Then if I subtract them, it becomes minus 14 centimeters squared per second. So I got my answer. The rate at which the area is changing is actually negative. So it means that I should expect to have this area shrinking actually over time, not increasing. So is that understandable?
Yes.
Okay, and I think it is also intuitively clear, yes, because one side is shrinking with higher speed, yes. The rate at which one side is shrinking is 3 centimeters per second. The other one cannot make it up, yes, because this is only increasing by 2 centimeters per second. So hopefully, intuitively, I think it seems correct that we expect that the rate at which the area is changing is a negative value, so it is decreasing. Okay, so I think this is a good example to remember and know on how to solve this problem. Okay, let me go to the next problem. This might be a little bit harder, but in the book there was a diagram for that. So I will draw the diagram and I wait for you a little bit, okay? I will probably only be able to solve this problem, but there are more problems. I will upload this, so yeah, 2 more problems. You don't need to work on them if you don't like to. These are a little bit harder than the level of the book. But this example, by the way, is comparable to the level of a question that I saw in the national test. Okay, but anyway, I will be able to solve this problem only for you, but I will upload this lecture notes to the Google Drive folder and below the video on the YouTube channel. So if you want to work more on it, you can work on them. Might be in the next session, I will solve them and put another video for you. Okay. Yes, you need to do all the pages in the book for the test on chapter 3. Okay, so let me read the question for you. So an aircraft is flying horizontally at a speed of 600 kilometers per hour. How fast is the distance between the aircraft and a radio beacon increasing 1 minute after the aircraft passes 5 kilometers directly above the beacon? Okay, so might be by just reading the words, it was not clear in the book itself. There was a diagram below that or next to it, but let me just describe it for you. So here, assume that this is, I don't know, this is the ground or somewhere. So here, yeah, we can make it more artistic, yes. So let us keep this the ground. And then what you have here, so assume that this is your beacon, or actually a sign or whatever. So this is your beacon. And then an aircraft is flying horizontally at a speed of this. How fast is the distance between the aircraft and a radio beacon increasing 1 minute after the, okay, what does it mean? It means that the airplane is flying in, for example, here, okay? And this is 5 kilometers directly above this beacon. But of course, this airplane comes here. Here, it is exactly 5 kilometers above the beacon, but it continues with the same speed, 600 kilometers per hour. And then the question is that, what is the distance, how fast is the distance between the beacon and the airplane is changing when 1 minute has been passed after this point? So let me just repeat it. I think it was bad. So the airplane is flying in this. It comes here, it is 5 kilometers, but it will continue flying. After 1 minute, this airplane is at some point. The distance from the airplane from the beacon at that particular point is this amount. But of course, this airplane is continue moving and the distance is increasing. You see, this distance, this length is increasing. We want to see how fast this length is increasing. I don't know, is that understandable somehow, the question?
To me, it's understandable.
Okay, good. So what I do, let me just draw a rough picture now. So for example, let me draw this as the line that the airplane is flying. Okay, and then assume, let me draw this one as well. So this is 5 kilometers. When we say distance, we always mean vertical distance. Okay, so this is the distance. And then, for example, after 1 minute, the airplane is here. So let me write airplane. And then we are interested in to see how fast is this distance is changing, because over time, this distance will change, yes? Oops. Yeah, that's good. Okay, so I want to find how fast this distance is changing. So how should I solve the problem? Do you have any idea? What is your target function here? Because otherwise, if you don't think in this way, you will be completely confused and lost. You shouldn't be scared of the problem. It's not clear in the beginning, but you need to read the problem and see how fast is the distance between the aircraft and a radio beacon. Okay, this distance is the target function. So let me call it D for the natural reason, distance function. This is my target function. Then you need to find an equation, a relation for D based on what you have in the problem. Okay? Of course, you have one variable in this problem. The variable is this one. This is your variable. Let me call it X. Because over time, this distance is changing, giving rise to a change in D. So this becomes clear. I need to find a relation between D and X. But can you see the geometry is very simple? Can you see that relation?
We can find it using the Pythagorean theorem.
Exactly, thank you, thank you. So what I do is that D squared is equal to what? 5 to the 2 plus x to the 2, okay? So then let me write it in this form. D squared is 25 plus x squared, okay? And then what I do, I'm looking for D. D in principle is plus and minus when I take a square root. But I don't need the negative sign because in this context, D is the distance and cannot be negative. So even though I have to put plus and minus algebraically, but I know that in this context, negative doesn't make sense. So then I have my function, but this is a function that relates D to X. Now I understand this is not a good notation because this D will be be confused with the D for this. Let me make it capital D. So let me make this capital D, because then otherwise this D will be confused with the D for the Leibniz notation. So this becomes D squared. Oops, sorry, D squared, and then this is D squared. This is D. Okay, but by reading the question, you want to answer how fast the distance is changing. So what you want to have D of D over time. This is your question mark. But here you have D expressed in terms of X, not time. So, but X, X itself depends on time. So D depends on X, X depends on time. So if you go back to that lesson, you will realize that I have drawn these diagrams. D depends on X, X depends on T. I want to find the derivative of D with respect to T. Do you remember what should I do? I should write D with respect to let me write this one for you. D depends on X, X itself depends on time, but my question is not D with respect to X, my question is D the derivative of this with respect to time. So this means that I go to the intermediate variable dx, but I need to remember to multiply by the derivative of the intermediate variable with respect to the last variable. So please let me know if you have problem with that. This is one of the lessons. If you have forgotten, you can go to the lecture after for the applications of the chain rule. There I talked about this rule. But that was what I wanted to mention here. If you have the sequence of variables like that, and if you are interested in the derivative of the leftmost quantity with respect to the rightmost quantity, you take the derivative of that quantity with respect to the intermediate variable, and then you need to remember to, because of the chain rule, to multiply by the derivative of the intermediate variable with respect to the rightmost variable. This is essentially what I told you in that lesson. So hopefully you understand what is going on here. Okay. But now let us try to see what we can do. If I ask you what is dd over x, you don't have any problem. This is a very simple chain rule problem. Okay, so what should I do? I would write, do you remember what is the formula for a square root of u prime? It is u prime divided by 2 square root of u, but u prime is just 2x. So let me be quick. So it becomes 2x divided by 2 square root of, I'm sorry, I don't know, sometimes this happens. So a square root of x squared plus 25, and then multiplied by dx over dt. This is my question mark. Okay, now can you help me to fill up the numbers? So let me make it smaller so that you can read the text as well. Okay. So in order to be able to answer this question mark, I need to put numbers here. But can you read the text and tell me what should I put for x here and there, the same x, and what should I put for dx over dt here? Or how to find them, if that is not directly given in the problem. I think you can tell me this one first. Is that clear for you? How do you interpret this? This needs your understanding about derivative. This means the rate at which x quantity, the rate at which this quantity is changing over time. You need to know a little bit of physics, of course, but I don't think that's hard. What is the rate at which this distance is changing? This represents what?
The speed of the plane, which is 600
exactly. Is that clear
kilometers
for
per hour.
everyone? Is that, yes, exactly, thank you. Is that clear for everyone that the rate at which this distance is changing is nothing except the speed of the airplane? Do you agree? If you disagree, complain. Otherwise, I will take it as agreeing. Yes, agreement. Okay, so this one is nothing except 600 kilometers per hour. But now can you tell me what should I plug in for x, or how should I calculate the x?
The distance after 1 minute.
Exactly. How do you calculate that?
600 times 1 over 60.
Exactly. So that is very good. So hopefully every one of you knows. So x after 1 minute is equal to the speed of the airplane multiplied by time. 1 minute is 1 over 60 per hour. So you need to write it in terms of hour, yes? 1 minute is 1 over 60 hours. And then this becomes clear. So this and that one are canceled. So I will get 10. This one and that one also cancel. I will get 10 kilometers. Yes. So the answer becomes x becomes 10 kilometers. And then I plug everything there and I get my question mark, as simple as that. And if you don't mind, let me put the units at the end. Of course, what is your prediction about the unit? It is clear. The quantity D is measured in kilometers. The quantity T in this problem is measured in hours. Yes, I have to fix all the units the same. So this would be kilometers per hour. Okay. So let me write everything. So by the way, this 2 and that 2 are canceled. So this x is 10. I would write 10. In the denominator, I will also write square root of 10 squared plus 25. Instead of dx dt, I put 600. And then I remember this becomes 6,000. In the denominator, I will get square root of 125. Then I need to know that this would be kilometers per hour. And then if you want, you can just simplify this number a little bit. I prefer to keep it in exact form unless you want to have a real approximation of this. So square root of 125 is 5 to the 2, 5. And then I take the square root, it becomes this. And this 5 and that one are canceled. So it becomes 1,200 over square root of 5 kilometers per hour. And I always prefer to get rid of the squares in the denominator. So do you remember? Let me just repeat this. We don't have enough time to go to another problem. Let us at least complete this one. I will multiply this by square root of, I rescale it by this to get rid of this square root in the denominator. So it becomes this one divided by 5 kilometers per hour. And then if I divide this by 5, it becomes 240. So this means that the question mark that I was looking for is just 240 square root of 5 kilometers per hour. Okay, so this is also something I wanted you to know. And this will complete that deficiency in my lecture there, that I only gave you one simple question. I solved you only one single question. Of course, the questions in the book are simpler than this, but these problems, I have seen something similar to them in the national test, of course. So if you want to see, the questions are on page 87 and 86. They are simpler than the level of the questions that I solved here for you. But that's also it's good to go and review your memory. You review your knowledge in that page, 86 and 87. Okay, any questions? Nothing? Okay, so let me pause this video